The torque output of an electric motor. An electric motor consumes 9 kilojoules of electrical energy in 1 minute. If 1/3 of this energy goes into heat and the other forms of internal energy of the motor, with the rest going to the motor output, how much torque will this engine develop if you run it at 2500 RPM? So the power consumed by the motor, is basically equal to electrical energy consumed per unit time. This is by definition of power. So we're consuming 9 kilojoules of electrical energy, 9 times 10 to 3 joules in 1 minute, which is 60 seconds. So that gives us 150 watts. And we're using 1/3 of this energy for heat and other forms of internal energy. The rest is going to the output. So therefore, the power output of the engine, will be equal to 2/3 of 150 watts, which will be equal to 100 watts. Now I want to remind you that the power is the work done per unit time. So it is F dot dx divided by the delta t, the time it takes to complete this work. And this is for a constant force, F dot product dx delta x over delta t, which is equal to the dot product of the constant force with the velocity. So this is for constant F. And that's the translational power. Now, if we have rotation, the work done by the torque is equal to integral torque dot d theta per unit time divided by delta t. And if we have a constant torque, this will be equal to torque dot delta theta over delta t, which will be equal to torque dot omega. So now this is when we have a constant torque. Okay, so having remembered these results, we have an angular frequency omega, which is 2 pi times the frequency f, and we have 2500 revolutions per minute. So this will be 2 pi times 2500 divided by 60 seconds. So this gives us 500 pi divided by 6 radians per second angular speed. Now the power output is equal to the constant torque tau times omega, tau and omega in the same direction. So this will be tau times 500 pi divided by 6 and this must be equal to 100 watts. So we can calculate the torque output as 600 divided by 500 pi, which is equal to 0.382 Newton meters. Okay, so in this problem we worked on power. Power in translational motion when you have a constant force is equal to F dot delta x vector divided by delta t, the time interval in which we have the force being applied causing the translation, that is F dot product with the velocity v. In the rotational case, it's torque delta theta divided by delta t. Torque d theta is the integral of torque d theta is the work done by torque, and this will be for the constant torque case, torque dot product with omega. So omega is 2 pi times the frequency, where the frequency is 2500 rpm, so it is 2500 divided by 60, and the output power will be equal to torque times omega, and this gives us torque as 0.382 Newton meters. So we were looking for the torque output of this engine when we run it at 2500 rpm, and this is the final result we obtain using the power output equals torque omega relationship.